Hi guys, so just a short video to show you a demo about Hooke's law. So Hooke's law says that the strain is proportional to the stress. So the strain will be the amount of deformation of an elastic body. And here I have a spring. So the strain is proportional to the stress. So the stress is the force applied. So in this case, Hooke's law says that the amount of stretch I'm going to get here will be proportional to the amount of force I'm going to apply here. Okay, so as you add more weight here, you see there will be a restoring force here, pulling in the opposite direction. So right now, the setup here, I have a spring and holder. It's being, that mass here is 50 gram, and it's in equilibrium between the weight pulling down and the restoring force. But you see how it's calibrated, so you want to focus on the little stick here. You see it's at a 0 mark. Okay, so because I have calibrated the system, then there is no strain, there is no stress. Now I'm going to apply a force. So that will be your stress. So I'm going to put here 20 gram. So 20 gram. So the weight is pulling down. The restoring force is pulling up. And you see that if you look at the marker, I get about one centimeter. So if the stress is 20 gram, then the strain, so the amount of deformation, which is in one dimension here, is just 1 centimeter relative to the equilibrium here, the 0. So now I'm going to add 10 gram. So I'll add 10 gram. So now I have 30 gram together. So that's 30 gram. So that will be your stress. And if you look at the marker here, I get about 2 centimeters. Okay, so you really have to look at the marker that I have here. So it's easy to make a parallax mistake, but it's about 2 centimeters, right? It's supposed to be 2 centimeters. So 2 centimeters. So I'm going to add one more. So now I have 40 gram. And if it stops moving, you see that the marker is at about 3 centimeters. So here I have 3 centimeters. So keep going. There will be a threshold when the spring gets deformed and then Hooke's law doesn't work. So again, the weight is pulling down, the restoring force is pulling up. You want to look at the marker. So now I have 50 gram. And if you look at the marker here, you see it's at the 4 centimeter mark. It's just that it's moving a lot, but it's 4 centimeters here. And I can add one more, not too much because it's a very small spring. So I don't want to overstretch. So now I have 60 grams. And you see that you have about 5 centimeters at the mark. So if you can see the marker here, it's about 5 centimeters. So what do you see here is that for each step here, each step of 10 grams, so each time you increase by 10 grams here the stress, so the force applied, here the stretch, So by the amount by which it's being stretched, so that will be the strain, increased by 1 centimeter. And each step of 10 grams here, you get 1 centimeter. Okay? So that means it's proportional to each other, right? So that means that there is a linear relationship, so it's a proportion between the strain, so deformation, and the stress, so the force applied. That here is the slope. So the slope is, it's going to be 1 centimeter per 10 grams. Okay, so let's do a graph. So let's make a graph. It's just to give you an idea, okay? I'm not doing things with high precision here. I started with 20 grams because 10 grams, that my spring was too stiff to react to 10 grams. So let's make a graph here. So here I have X will be the stress. So stress is in grams. So that will be the force applied. Here I have a strain. So the strain is just the stretch. The unit is centimeter. And I started with 20 grams. Okay, because here the spring was not good enough. I don't have enough precision. So 10 grams, and I get a stretch here of 1 centimeter for 20 grams, right? Then here I add 10 grams, so that will be 30 grams. I don't have to put the gram because I have it here. It's okay. So for a step here, from here, a step here in 10 grams, I'm gonna go up again, okay, by another 1 centimeter. Then another step here, which is 40. So that's going to be 40 here. So 40 here. Okay, a step in 10 grams, you're going to go up again by the same amount here. And then 50, same thing for a step of 50, of 10 grams, you go up here. So what you get here is a straight line. For each step of 10 grams here, the stretch here is going to increase by 1 centimeter. So that's going to be your delta X. That's going to be your delta Y. So this is the definition of the slope, rise over run. Okay, so that means that your slope, delta Y over delta X, equals 1 centimeter per 10 grams. Okay, so that means we just we were able to verify Hooke's law, even though my material is super cheap and not very sensitive, but you get the idea. Now, in your textbook, it says F equals K delta X. So that's going to be the force. The unit is in Newton. Delta X, the unit is in meters. And this here is a constant. So that's your slope. Not the same as this one, but it's also a constant. This is actually 1 over K, but you have to fix the unit. So that's what we're going to do. But in your textbook, that's how Hooke's law is expressed for a spring or a rubber band or anything in one dimension. Okay, so you see that K is the spring constant. It only depends on the stiffness of the spring, and it's going to be the force divided by delta x. So the unit of K is Newton per meter. And here I have centimeter per gram. Okay, so we're gonna arrange that. So 1 centimeter for 10 gram, that's gonna be the same thing as 10 gram for 1 centimeter. Okay, so that's gonna be in kilogram. So it's gonna be 0.01 kilogram over 0.01 meters. Okay, so my K now is 0.01 kilogram for 0.01 meter. Now I'm gonna have, so 1 kilogram per 1 meter. So it means that if you apply a stress of 1 kilogram, the stretch will be 1 meter. So if I want to have the spring constant, 1 kilogram is the same thing as about 10 Newton. So 10 Newton per 1 meter. So the spring constant equals to 10 Newton per meter. So you can write that the force, in that case, that will be the weight equals 10 times the stretch. So this is in Newton and this is in meters. So that's Hooke's law. Now you can use such a setup. So let's go back to the graph. So I have a graph here, right? So you can use that setup here to find unknown mass. So you can use that as a, once you have the calibration and you have your K, you can find the mass of unknown, right? An object with an unknown mass. So here, for example, I am at the 0 mark, okay? Now I have a tape and I'm going to use that as an unknown mass. So I'm going to place it here. It's just to give you an idea, right? And I can look at by how much it's going to be stretching. It's going to be about 1 point. It's more than 1. It's about 1, right? So 1 gram. It's about 1 gram. It's just to give you an idea. And so it's about 1 centimeter, I meant. So 1 centimeter here is 20 grams. So that means that object here is about 20 grams. So you can use that setup. Once it's calibrated, you can use it to find unknown mass.